In this video, we're going to talk about planes in 3 space. Now, the last video we talked about lines and parametric equations of lines. This video is about planes. Now, a plane in 3 space can be determined uniquely by a point in the plane and a vector that's perpendicular to or normal to the plane. So what do we mean by this? So I've drawn a plane here, and we have a point x naught, y naught, z naught that's on this plane. Okay, and in fact, you can imagine there are lots of planes that would go through, or that would contain this point x naught, y naught, z naught, right? You can imagine this kind of plane rotating around or wobbling around this point. There's lots of planes that go through that. I've just drawn one plane in particular that goes through that point. Okay, now once we have that point, how can we, and we have a vector here that's perpendicular to the plane, okay, or that's normal to the plane. Once we know that point and that vector, that determines what the plane is uniquely, right? If you imagine the normal vector kind of rotating a little bit, that would make the plane rotate as well. Okay, but once we have a point in the plane, x naught, y naught, z naught, and a normal vector to the plane, or a vector that's perpendicular to the plane, okay, it pops out at a 90-degree angle here, then that's enough to determine the plane uniquely. Okay, now I've also drawn kind of a generic point x, y, z in the plane. I could have drawn this point anywhere in the plane, but I've drawn it here, and I've drawn the vector that goes from x naught, y naught, z naught to x, y, z. And notice that the normal vector will be perpendicular to this vector right here. In fact, that'd be true no matter where I put the x, y, z. I could have put the x, y, z over here and drawn the vector from here to here. Could have put the x, y, z over here, drawn this vector. Any way you draw it, the vector, that vector would be perpendicular to the normal vector. In fact, that's really the definition of a normal vector here. Okay, so when we say that that vector is perpendicular to this, what do we mean? Well, this vector here has coordinates x minus x naught, y minus y naught, z minus z naught. Because remember that the vector that goes between 2 points, from this point to this point, you subtract the coordinates here. So x minus x naught, comma y minus y naught, comma z minus z naught. That's this vector. Now this vector will be perpendicular to ABC. So in other words, when we take the dot product, we should get 0. Okay, so notice a point x, y, z will be in the plane if and only if this vector that goes from x naught, y naught, z naught to x, y, z is orthogonal to or perpendicular to the normal vector. Okay, so again, I've just drawn one x, y, z here, but you can imagine any point in the plane here and drawing the vector from there to there. That would be perpendicular to this normal vector. Okay, now what does it mean to be orthogonal or perpendicular? It means the dot product is 0. So the dot product of this vector with this vector should be 0. So the dot product of x minus x naught, y minus y naught, z minus z naught with ABC should be 0. Okay, so if we actually do that dot product, what do we get? Well, we get x minus x naught times A, that's what we've written here, plus y minus y naught times B, that's right here, plus z minus z naught times C, that's right here. That should equal 0. Okay, so notice this is what's called the point normal form for the equation of the plane. Okay, it's the plane that goes through x naught, y naught, z naught, and has normal vector a, b, c. Okay, it's called a point normal form. By the way, that word norm or normal we use for all kinds of different things having to do with vectors. We talk about the norm of a vector, that's the length of a vector. To normalize a vector is to find a unit vector that's in the direction of that vector. And a normal vector to a plane is just a vector that's perpendicular to that plane. Okay, so let's do an example. Find an equation for the line that passes through 7, negative 3/8. So in other words, the plane, find the equation for the plane that passes through this, or in other words, this point is on that plane, and is perpendicular to this vector n, okay, 4, 6, negative 13. In other words, n is a normal vector to the plane. So how do we do this? Well, here's our formula. Oh, I forgot to put the equals 0 over here. But a times x minus x naught plus b times y minus y naught, and so forth. This equals 0. So plug things in. Well, the a is 4. So we have 4 times x minus 7 plus 6 times y minus a negative 3, or y plus 3, plus a negative 13 times z minus 8. Okay, equals 0. Okay, so this is the equation of the plane. Now we could distribute things here and write this as like 4x minus 28, and this would be 6y plus 18. In fact, I've done that right here. If I distribute the 4 and the 6 and the negative 13, we end up getting this right here. Okay, and then we could combine our constants that we have left over. We have still the 4x, the 6y, and the minus 13z. I've written that down here. But the negative 28 plus 18 and plus 104, that ends up being plus 94. So we have 4x plus 6y minus 13z plus 94 equals 0. Or you could subtract 94 from both sides and get this. But this is the equation of a plane. Now, what do we mean when we say this is the equation of a plane? Well, what we mean is that if you plot all of the ordered triples that make this true, so in other words, to find an ordered triple that makes this true, find some x value and y and z that makes this true, and you would have an ordered triple. That point would be a point on the graph of this equation. Then you find another x, y, and z that you could plug in that would make it true. That would be another point, another ordered triple on this graph. In fact, if you find all of the x, y, z's that make this true, all those points would lie along a plane. Right? So the graph of this equation is a plane in 3 space. Okay, and specifically, it's the specific plane that contains this point. Okay, it goes through this point and has this as a normal vector. Okay, but notice this has the form ax plus by plus cz plus d equals 0. And the a, b, and c were actually the normal vector. The a, b, c was the normal vector. Okay, and the d was what we ended up getting right out here. Okay, so here's a theorem. If a, b, and c are constants, with a, b, and c not all equal to 0, so at least one of them is non-zero, because otherwise you get, if the a, b, and c were all 0, you would just get d equals 0, and that doesn't even really make sense. Okay, if a, b, and c are constants, then the graph of ax plus by plus cz plus d equals 0 is a plane. Okay, it has the vector n equals abc as a normal vector. Okay, so anything of this form, so like 7x plus 3y plus 9z plus 53 equals 0, that would be a plane. Okay, the graph of that would be a plane. All the ordered triples, x, y, z, that make that true would end up lying along the same plane. Okay, so let's do an example. Determine whether the following 2 planes are parallel. And what we mean by parallel planes are planes that never intersect. Right? So usually planes would kind of cut through each other, right, in a line, but you could have 2 planes that are parallel to each other. Okay, so here are 2 planes. Are these planes parallel? Well, 2 planes will be parallel if they have the same normal vector, or the normal vectors don't even have to be the same. The normal vectors just have to be a multiple of the other. Okay, so in other words, if two planes will be parallel if they have parallel normal vectors. Okay, so if one normal vector is a multiple of the other. Now notice a normal vector for this first plane would be 3, negative 4, 5. Okay, we'll call that n1. n2, a normal vector for the other plane would be negative 6, 8, negative 10. And notice n2 is a multiple of n1. In fact, if you multiply each of the coordinates of n1 by negative 2, you get the corresponding coordinates of n2 here. Okay, so n2 is a scalar multiple of n1. It's negative 2 times n1. So n2 and n1 are parallel. In fact, they're facing the exact same direction, and well, really the exact opposite direction of each other. Okay, but that means these vectors are parallel. So the planes themselves that have these as normal vectors are also parallel. Okay. All right, now let's look at an example, and I think this is a really interesting example here. Find the equation of the plane that passes through the points P1, P2, and P3. So I have coordinates for each of these 3 points. And then put your final answer in this form. So notice if you have 3 points here out in 3-dimensional space, okay, as long as these 3 points aren't all on the same line, those 3 points should determine a unique plane. Okay, there'll be a unique plane that goes through those 3 points. Okay, and the question is, what's the equation, or what's an equation for that plane? Okay, so we have P1 was 2, 5, 1, P2 is 4, 7, 8, and P3 is 10, 3, 0. How do we find an equation for that plane? So the way I've drawn it here, it almost looks a little wavy here, but this is a flat plane. Just by definition, a plane has to be flat, right? So we have this plane. Okay, what is the equation of that plane? Well, remember, what are the 2 things you need to know about a plane to figure out the equation for the plane? Well, if you know one point in the plane, In fact, we know a point in the plane. We know 3 points in the plane. So we have more than enough information for that. You need a point in the plane, and you need a normal vector to the plane. Now, we weren't given a normal vector. So how can we do this? Well, we can find a normal vector by doing this. We could take the vector that goes from P1 to P2, and then the vector that goes from P1 to P3. If you take the cross product of these two vectors, you're going to get a vector that's perpendicular to both of the original ones. And that will be perpendicular to that plane, right? That will be a normal vector. Okay, so we're going to do P1, P2, find that vector, P1, P3, get that other vector, take their cross product, and that will give us a normal vector. So then we'll now have our point in the plane and our normal vector. Okay, so what is P1, P2? Well, subtract the coordinates. Take the coordinates of P2, subtract the coordinates of P1. So we get 4 minus 2 is 2, 7 minus 5 is 2, and 8 minus 1 is 7. Okay, so we get 2, 2, 7. That's P1. P1, P3, we subtract the coordinates. We end up getting 8, negative 2, negative 1. And then we take the cross product of those two vectors, 2, 2, 7, and 8, negative 2, 1. If you work out the details, so you do I times this determinant of this matrix and so on, and minus j times the determinant of this matrix here. If you work out the details, you get 12i plus 58j minus 20k. Okay, so in other words, the n, the normal vector ABC, is 12, 58, negative 20. Okay, that's our normal vector here. Okay, and our x naught, y naught, z naught, well, we could pick any one of these points, but let's just pick P1, will be our x naught, y naught, z naught. It's 2, 5, 1. Okay, that's what P naught, or P1 was originally. Okay, so notice we can just write this in our form here. A times x minus x naught plus b times y minus y naught, and so on, equals 0. And so plug things in. We get 12 times x minus 2 plus 58 times y minus 5 minus 20 times z minus 1, okay, equals 0. Okay, and you work that out, and if you distribute the 12 and distribute the 58, distribute the minus 20, we get this. And then we combine our constants together. We have a minus 24, a minus 290, and a plus 20. That ends up giving us minus 294. So this is the equation, 12x plus 58y minus 20z minus 294 equals 0. Now, how could you check your answer? Because it would be very easy to have made a mistake up here, messed up a minus sign or something, particularly when you're doing this cross product. It's easy to get something goofed up. How could we check our answer? Well, go back up to your original points and plug them into this equation, see if you get a true equation here. So for example, take P3. So if x is 10, y is 3, z is 0, plug it in. So plug in 10 for x, 3 for y, and 0 for z. Now notice if we do that, if we plug in 10 here, we get 120. If we plug in 3 here, we get 150 plus 24. We get 174. So we get 120 plus 174. That's 294. And then minus 20 times 0. Remember, z was 0. So we get 294 minus 0 minus 294 equals 0. Notice it's a true statement. Okay, in fact, try that for all these. Try it for P2 and for P1. Plug in these for x, y, and z and see if you get a true statement, and you should. Okay, that's a quick way to check your answer. And by the way, it's very easy to have made a mistake, so it's a good idea to check your answer. Okay, one other thing that the book talks about here is the distance between a point and a plane. So you imagine a plane and a point that's not on the plane. You could wonder, how far is the point away from that plane? So if you were to drop a perpendicular from that point down to the plane, okay, how far away would the point be from the plane? Okay, so any plane, and you have a point that's not in the plane, you want to find what's the distance there between that point and the plane. Okay, if you're given the coordinates of the point, x naught, y naught, z naught, and you're given this plane, the equation of the plane, turns out the distance is given by this formula. Now, why does this formula work? Well, I encourage you to look at page 720 to 721 in the book. It gives kind of a short little explanation. You have to think about it a little bit, what's going on in each step here, but I'm not going to explain it here in this video, but this gives us the distance formula, not between 2 points, but between a point and a plane. Okay, so now again, you might wonder, what do you mean by the distance from a point to a plane? There's lots of different points in the plane. Well, there's one point in the plane, there's one unique point in the plane that would be closest to that point, x naught, y naught, z naught. And so the question is, what is the distance between those 2 points? Okay, that's what we mean by distance from a point to a plane. Okay, so let's do an example. What's the distance between the point 1, negative 4, negative 3, and the plane 2x minus 3y plus 6z equals negative 1? Okay, well, this point is our x naught, y naught, z naught. And our ABC, notice, is 2, negative 3, 6. Okay, and by the way, our d is 1. Why is our d 1? Well, remember, the equation had to be of the form ax plus by plus cz plus d equals 0. So we don't have an equal 0 here. We need to add 1 to both sides. So notice the d ends up being 1, and we have to use d in our formula here. Okay, so if we plug things in, the capital D, the distance, will be, well, our ABC, remember, was 2, negative 3, 6. So we put 2 times negative 1, or I'm sorry, 2 times 1 plus negative 3 times negative 4 plus 6 times negative 3 plus 1, that's what our D is, all over the square root of a squared plus b squared plus c squared. Okay, and our ABC, again, was 2, negative 3, 6. Well, if you work out the details, you get negative 3, and it's really the absolute value of negative 3 over the square root of 49, so it ends up being 3/7. Okay, so that's a little less than 1/2. So actually, this point is very close to actually being in the plane. Okay, this point is very close to that plane. It's only a distance of 3/7, so about 0.4, whatever that is, distance from the plane. Okay, now one last thing here is, how do we find the angle between two planes? Okay, what do we even mean by the angle between two planes? Well, if you look at these two planes here. Notice these two planes intersect in a line here. Okay, in fact, that'll always be the case for planes unless the planes are parallel. If you have two planes that are parallel, they'll never intersect. Or if the two planes are the same plane, they intersect in the whole plane. But you can never have two planes intersecting at just one point, right? The planes will always, if they intersect and they're not the same plane, they'll always intersect along a line here. Okay, but we could talk about what's the angle between these two planes, and what we mean by angle is this angle here. Now, you could also talk about the angle on the other side here, like this angle. And that would be the obtuse angle between these two planes. So if this angle were, say, 50 degrees, this angle would be 130 degrees, right? Because obviously it has to add up to 180, right? And so if we want to find this angle theta, this acute angle between the planes, how do we do it? Well, notice that if n1 and n2 are normal vectors to the plane, so I've drawn these right down here, then the angle between the planes will really be the angle between these normal vectors. Now notice n2 is normal to this plane right here, right? n1 is normal to this plane right here. But the angle between those two vectors is the angle between those two planes. Okay, well, if the angle ends up being obtuse between n1 and n2, like if I draw an n2 on the other side, what we would end up getting is the bigger angle. So like if this were 50 degrees, this would be 130 degrees. We get the obtuse angle. Okay, so in other words, if the angle ends up being obtuse, then the acute angle will be the angle between n1 and negative n2. Okay, so the point is the angle between the planes, those, is like the angle between these two normal vectors. So it's cosine inverse of n1 dot n2 over the length of n1 times the length of n2. Now, there are absolute values here in the numerator, and again, that has to do with the fact that we want to find the acute angle between the planes, not the obtuse angle. So if we didn't have the absolute values, you end up getting a negative number, you would end up getting the obtuse angle between the planes. Okay, so let's consider these two planes. Okay, 2x minus 4y plus 4z equals 6. And again, all the ordered triples that make this true. For example, the ordered triple 1, 0, 1. Right? If x is 1, y is 0, and z is 1, that would make that true. 1, 0, 1 would be a point in this plane. Right? Or 3, 0, 0 would work, right? All the ordered triples that make this true would be a plane. Okay, and then let's also look at this plane here. How do we find the angle between these two planes? Okay, so these two planes are going to intersect at a line. How do we find the angle? Well, we're going to use this formula. We find an angle between their normal vectors. Okay, so n1 is going to be 2, negative 4, 4. Okay, and n2, the normal vector to this plane, will be 6, 2, negative 3. Now notice the norm of n1, which we need to find, is the square root of 2 squared plus minus 4 squared plus 4 squared. Ends up being the square root of 36, so I rigged that up to give us a nice number here, because that's just 6, so we don't have to deal with square roots. n2 is going to be the square root of, the norm of n2 is the square root of 6 squared plus 2 squared plus minus 3 squared. Again, I rigged it up to be nice, so we get just the square root of 49, which is 7. Oh, and n1 dot n2, if you dot these two vectors together, it's 2 times 6 plus negative 4 times 2 plus 4 times negative 3. It ends up being 12 minus 8 minus 12. It ends up just giving us minus 8. Okay, so theta is cosine inverse of -8 over 6 times 7. And again, it's actually absolute value of -8 over 6 times 7. So it's cosine inverse of 8 over 42 gives us 1.379 radians, or 79.02 degrees. That's the angle between these. Now, if we had left off the absolute values there, if we'd forgotten the absolute values, what we would end up getting is about 101 degrees. Okay, because notice 101 plus 79 is 180. Okay, so if we had kept it as a -8, we would get 101 degrees. But we wanted to find the acute angle between the planes. So it's about 79 degrees. Okay, one last thing in this video here. Consider the line L of intersection between these two planes. So this line right here. Okay, how can we find a vector that's parallel to that L? Okay, how can we find a vector that's in the direction of this line of intersection? Okay, now notice if we took any vector, so let's say a vector starting at this point and going along this way in this direction, it doesn't actually matter how long it is, wouldn't that vector be perpendicular to both n1 and n2? Okay, if you visualize, it's a little tricky to visualize because it's three-dimensional space. Or if it started here and started going in the opposite direction here, wouldn't that vector be perpendicular to both n1 and n2? In fact, that's a way to characterize this line, is the direction of this line, is if you start here and go in this direction, that will be in the direction of the line if and only if that direction vector is perpendicular to both n1 and n2. Okay, so how do we find a vector that's perpendicular to both n1 and n2? Well, can't we just take their cross product? If we do n1 cross n2, that'll give us a vector that's perpendicular to both of these. So that'll be a vector in the direction of that line. That's if we did n1 cross n2. Or if we did n2 cross n1, we'd also get a vector. It'd be in the exact opposite direction here, but that would still be parallel to that line. A vector that's parallel to the line or in the direction of the line. So all we really need to do is just find n1 cross n2. Okay, or n2 cross n1. Okay, so let's do that. n1 cross n2, well, n1 was 2, -4, 4. n2 is 6, 2, -3. We take the cross product, we get this vector, 4, 30, 28. Okay, that would be a vector that's parallel to this. And in fact, any multiple of that vector, whether you made that vector longer or shorter, that would also be a direction vector, or even multiplied by a negative number, so it's in the exact opposite direction. That would be a direction vector for that line. Okay, so if you do n1 cross n2, that will be a direction vector for the line of intersection between these two planes.